As Greg mentioned, the 35th year of the Flagstaff Festival of Science, and to my understanding, this is the longest running Festival of Science, free, open to the public, continuously ongoing in the known universe. So that is a really exciting thing that we get to have here in this little small mountain town of Flagstaff, Arizona. So thank you all for coming. It's really exciting to get to talk about science. I really love talking about geology. Working as a researcher, we really don't get to talk about the fun stuff. A lot of it's nitty-gritty details and dealing with numbers and statistics. So this is really fun. And to begin that with a question, do we have any geologists or earth scientists in the audience? All right, in the back. All right, we got one. Great, awesome, that is wonderful. So now I know I have some fact checkers in the audience, so I just can't make stuff up if I think it's entertaining. But in geology, we use a lot of puns. I like to tell some geology jokes to think, make it a little entertaining, because the science of geology has a lot of jargon. And you don't need to understand the terminology to go out on your hikes and appreciate nature. And living here, or at least visiting here in a place like Flagstaff, Northern Arizona is a true gem for geologic wonders. Hence why I titled this talk, Geologic Wonderland, the fascinating geologic story of Northern Arizona. And this link for the survey is important. We were asked to put that out here, and I'll have this link here at the end of the talk again, so you can refer to that again. It does help the Festival of Science continue to grow and continue to do well. Also, we'd like to thank our sponsors, as this is a free festival. That just means someone else is paying for it to make it happen. So there's a lot of great sponsors in Flagstaff. But it's not just the sponsors giving money to keep the lights going for this festival. It's really the volunteers, such as Greg, who introduced me, and Brandon Lurie and Lori back there. It really is a team effort. It takes a village. Most everyone who works on the board of the Flagstaff Festival of Science is a volunteer, volunteering their time because we love doing what we do. So a little background about myself, so you might take me seriously. I have a bachelor's in science and master's in science in geology from Arizona State, and then a master's of geography and geospatial sciences from NAU, Northern Arizona University, also known as the Harvard of the Colorado Plateau region, which I'm proud to say, the greatest university in the Four Corners states. And I've worked as an instructor teaching geology and geography at the college level, worked as a researcher, as a geologist, and now I'm very honored to be a geographer working here at the USGS in Flagstaff. So the outline for our talk today is we're going to go over some basic geology foundations, some geology 101 type material. Then we'll talk about the landscape of Arizona geography, kind of how the landscape got to be where it is. Some of the differences between geology and geography is that geography is really focusing on the surface of the earth, and geology is underneath the surface, what is going on with those processes and materials, and then how do they interact with the surface to make it within the realm of earth science. Or here in this USGS planetary building, astrogeology, a lot of the planetary bodies in the solar system are also studied here in this building using some of the same principles of geology and geography found on Earth applied to other planets. So this building you're in is a very exciting place, which we'll talk about a little bit more as we get further on into the lecture. And then we'll go into a little bit more detail about the geology of Northern Arizona. The biggest challenge will be trying to keep this presentation less than an hour, because I could be here all night talking about the geology of Northern Arizona. So we can continue our conversation at the star party if I get a little too enthusiastic and just keep going and I need to be taken off stage. But one concept I like to talk about before we get started when we're understanding the geology of Northern Arizona is the concept of geologic time. Geologic time is something that is challenging even for geologists to help understand. So often when we're teaching geology, we like to put it into a different context. Geologists, in addition to talking with our hands, we also like to go into metaphor land quite a bit. For example, If you were to take the whole entire history of the Earth, if you extend your arms and I say my right hand represents the beginning of the formation of the Earth out there in the solar system, my left hand, the tip of my fingernail, represents where modern humans came into existence. Where about the dinosaurs came into existence would be about my left wrist. And another way to think about that is this great system that I saw posted on the Grand Canyon National Park website, where they break the timing of Earth history into a year on Earth. So if you begin January 1st, which geochronologically estimated about 4.5 billion years ago, all the way up to modern day, we say the Earth first began on January 1st. And then where would that put us? We as modern humans wouldn't come into existence until about December 31st at 11:59 p.m. If you start to break up this time, that about 4.5 billion years into 12 months, that is about 383 million years per 1 month. Or each day represents about 12.6 million years. So we're looking at that whole early history of Earth. For much of the beginning of Earth's history, there was no known life on the planet. And then gradually fossils started to appear in the record. And we all loved dinosaurs as a kid. Some of us still do, myself included. We think about the dinosaurs as ancient creatures that roamed our planet. On this time scale, they didn't really come into existence until about December 15th. And all the way going from January 1st all the way to November 19th, the 11th month of the year, is really when we start to see a lot of the rock units northern Arizona is known for. When we see what the period of time known as the Cambrian, that would be the bottom layer of what is known as the Paleozoic sediments we see in the Grand Canyon. And moving into that, the next geologic time period, the Permian, would end about December 12th in that geologic time period, where many of the rock layers you see in the upper sections of the Grand Canyon, rock layers you see when you go to Sedona, or below our feet here in some regions around Flagstaff, below the volcanic rocks, would be in that time span. So geologic time is just something that is really incomprehensible, but if we break it down into a timeline of a day, it's something we can really understand, I think, a little deeper when we put it like that. And the next topic to discuss is how the Earth works. As I said, geologists, we like to talk with our hands and use metaphors. Well, food is a great one. If we think about the layers of the Earth, we can think of it like an egg. So if we're doing some cooking and we crack an egg, that egg yolk represents the core of the Earth. And you can think of that as a dynamo heat engine. That is producing heat. There's radioactivity, it's releasing heat, and that is moving up through the mantle. And we can think of the mantle as the egg white, representing a majority of the egg. And then we get to the very top, a very thin layer, which if I ask a question, what is a geologist's favorite part of the pizza? The crust. The crust, where we live on here on Earth, the very thin veneer of the surface of the Earth known as the crust, where all of the geologic wonders that we see are because what is underneath us is moving and generating heat. And you can think of the Earth behaving like a lava lamp, where hot things are rising, and as heat rises through the mantle, it can break through the crust and cause the crust of the Earth to break apart into different plates, which we call continents, and which form the theory of plate tectonics, which in the field of science is a relatively new theory, only really being widely accepted in the last 50 or so years, when if you saw geology textbooks from, say, the 1950s, it still might be considered just a hypothesis that was out there. So when we think about other fields of science, like physics and chemistry, that have had long-standing, we think of Newton's laws of motion, that's been around a few hundred years. But the science of geology is still continuing to evolve, and discoveries are still being made, which is quite fascinating. So we have that heat moving from the core through the mantle up to the crust. And that causes the plates to move around. And when those plates move around, there's continental plates that are lightweight, and we can think of them as floating. And then there's oceanic plates, which are dense, and we can think of them as sinking. And as the plates are moving around the planet, the heavy plates will subduct under the lighter plates, and that can continue to create heat and more friction. That can cause volcanoes, that can cause mountains to form. If two plates collide, that can cause plates to buckle. If they're continental plates, that can form mountains. Plates can spread apart and form volcanoes. And we put this into the context of geologic time. These plates move at about the rates your fingernails grow. So we're only talking about millimeters per year. So when you go to trim your fingernails, you can think that's how far the North American plate that I'm standing on has moved since the last time I did that. And as this process continues to happen, it leaves us with something known as the rock cycle. So there's three main types of rock. Does anyone know those three main types of rock? So I heard sedimentary, metamorphic, and igneous. And I said type of rock, so you're all wrong. I was thinking alternative, classic, heavy metal, punk, country. But I was hoping someone would give me an answer like that, but that's okay. But yes, in geology, yes, that is absolutely right. We have three main types of rock. We have igneous, sedimentary, and metamorphic types of rock. And through this diagram here, through those processes of the plates moving around and causing some rocks to subduct, some to lift up, and then the processes of erosion, some rocks get buried, they get exposed to heat and pressure, they turn into different types of rocks. Over geologic time, the Earth is changing, the Earth is moving. We can think of geologists like detectives at the scene of a crime, and we're trying to figure out what happened here, and our clues are things like deposition, erosion, mountain building, earthquakes, volcanoes, trying to figure out how these rocks got here, how to make sense of the landscape as a descriptive science. So when we take a look at some of these terms in a little more detail, this terminology doesn't have to be so complex. When we hear a term like igneous, we think, where have we heard a word that sounds similar to that? Ignite, exactly. So if we think ignite, we can think fire, rocks that have been melted, rocks that used to be in a liquid state because they were heated up, forming a molten lava on the surface or a molten magma below the surface, and then that cools down as it either becomes on the crust or closer to the crust underground, and then those little minerals that are hot molten lava start to cool or crystallize and become solid, and that can form the igneous rocks. And there's two different types. When we think of intrusive igneous rocks, meaning they form below the surface, they can develop these big crystals in them. And some of you may have granite countertops at home, or you might have friends that do. So next time you're at a dinner party, you can impress them by pointing out the different minerals based on their cooling size, based on the relative size. If they're large minerals, that means they cooled rather slowly. If they're very tiny minerals, crystals, that means they cooled very fast. So when you're pointing out these minerals such as hornblende, biotite, plagioclase, feldspar, quartz, it can make some great dinner party conversation. And we can see those rocks more down in the valley. We don't see granites or many rocks like that up in the Flagstaff area. But there is a volcanic rock that is plentiful around here, right around here, another rock where it cools so fast you would need a magnifying lens to actually see the crystals in it. And this rock we see, this dark black rock, anyone know what it's called? Basalt. So don't take a rock for granted because it might be a basalt. This rock is very important to Flagstaff because of our geologically recent volcanic history in the Flagstaff area. So if you just walk out here to Buffalo Park, you'll find this rock. If you go to downtown Flagstaff, you'll see a lot of the old historic buildings were built from this rock because it is a very plentiful rock. and this meant that it cooled very quickly on the surface. Our next phase of rocks, sedimentary rocks, and we think of the root of this word, sediment, so formed from different pieces of other types of rock. Often if you hear a rock with the word stone in it, what are some rocks with the word stone in it? Sandstone, limestone, mudstone. Those are rocks that are most often sedimentary in nature. And those are formed from pieces of other rock coming together, lithifying to form a sandstone or mudstone. That's a great question. And you must be in the advanced class because we're going to get to that next. So in sedimentary rocks, there's two types. There's the ones known as clastic, meaning they're forms of clasts, or pieces of other rock, such as sandstone made of sand, mudstone made of mud particles. This picture here known as a conglomerate, made of little fragments of gravel-sized rocks. And the other type of sedimentary rock is a limestone, which is formed in the ocean. And that is from a biochemical precipitate. When we think of the ocean, a shallow marine environment, a coral reef, there's a lot of little shells and coral fragments that have hard parts made of calcium carbonate. When all those shells and coral fragments and planktons settle to the bottom of the ocean, they fuse together over time and form this biochemical precipitate, which goes on to form limestone. So yes, some sedimentary rocks are formed in the ocean, such as limestone. Some are formed on land, such as sandstone and mudstone. However, sandstones and mudstones still can involve water. It's just most likely fresh water on land or close to the ocean in a beach environment. But when you see limestone, you can think, aha, this landscape used to be an ocean. And many of the geologic wonders found in Flagstaff or in the surrounding northern Arizona region are our beautiful sedimentary rocks that you see in the Grand Canyon in Sedona and below our feet here in Flagstaff. The next type of rock, this rock up here, for the geologists in the room, this is very gneiss. This is a rock spelled with a silent G, spelled gneiss, G-N-E-I-S-S. And another rock called a quartzite. These are rocks that you can think of, they went through a chemical change, similar to if you were to take a soft clay and put that into a kiln, it would be heated up and come out as a ceramic. You didn't add any new elements, you didn't take away any molecules, but that heat, or in the earth, if it gets buried, the pressure can change the mineralogic structure and fuse it into a different type of rock. And those rocks are known as metamorphic rocks. So if you think the root of that word, to morph, metamorph, to change, a metamorphic rock used to be a different type of rock. And these rocks are very solid, very dense, very resistant to erosion. So these are great mountain-forming rocks. We don't have many in the northern Arizona or Flagstaff area, but if you go down to the valley, to Phoenix or Tucson, western Arizona, there's great examples of mountain ranges made out of these types of rocks. We would only see their eroded remnants here in the forms of sandstones and mudstones up here. So out of the rock cycle, the three main rock types, we have 2/3 of them represented, just what we can see in the Flagstaff area. You might see some metamorphic rocks, maybe in some landscaping or some stone carved out of granite. The next step to understand, now that we know how the rocks got here and what our major rock types are, so you can impress your friends on all your hikes from now on, is to understand the geography of Arizona. So if we look at this topographic shaded relief map here that's in different colors, we have the green areas higher elevation, the tan and brown areas lower elevation. And if we just take a look at the map of the state based on elevation, do we see any major changes in elevation? It appears that most of the northern and eastern part of the state is at higher elevation, and the southern and southwest and western parts of the states are at lower elevation. And the region where we live in Flagstaff, where there's a white part in there that shows some mountain peaks that are the highest elevation. We are right on this high elevation plateau known as the Colorado Plateau, where a lot of our geologic wonders are found. We'll talk more about this later, but it's basically a layer cake of geology that was uplifted above the surface with the story to tell. And then down to the south in the Phoenix and Tucson areas, we have a geographic province known as the Basin and Range, where the crust has been pulled and thinned and pulled apart. And then right in between those areas, when you think of cities that would be in that range, in between those two landscapes, places like Prescott, Payson are right on the edge, Sedona is right on the edge. Geographers were very creative with this landscape and broke this up into 3 zones. We have our Colorado Plateau to the north, Basin and Range to the south, and creatively named the transition zone in between. And when you go to Sedona, who here has been to Sedona? All right, when you're in Sedona, you are on the edge, you're looking up at the Colorado Plateau. And Sedona has great exposures of these rocks because they've been eroded relatively recently, and it's a desert environment, so you can see the rocks there. A beautiful place to see the stratigraphy of Arizona, where you can read each chapter, each layer of rock like a chapter in a book. So this is a geologic map here. There's not going to be a quiz on it, but each color represents a different type of rock. And in the north and east in the Colorado Plateau, with the blues and the greens, we have a lot of the sedimentary rocks that are spread out through the region. Things like sandstones and limestones. In the southern part, we have rocks that are in more fiery colors, reds, oranges, yellows, in between a lot of white. Well, those reds and oranges are igneous, volcanic rocks, older rocks, some metamorphic rocks, and in between all that white is just a term called alluvium, which just means relatively recent dirt that filled in the valley floor. And if you look at a diagram, a cross-section of what the valley might look like, it's all these separations of valleys and basins. When we say the valley, meaning the Phoenix area, it's not actually surrounded by a circle of mountains. There's a series of mountain chains that make up the valley with basins in between. And this is because in this area, the landscape was pulled apart through tectonic processes. So in the last 30 to 60 million years or so, the crust was pulled apart. And as it was pulled apart, it was thinned. And that's why the elevation in Phoenix is about 1,000 feet above sea level. And then here in Flagstaff, you're at about 7,000 feet above sea level. So in only a drive that takes you about 2 hours, you're traversing over a mile in elevation change, which explains why the climate is so different between Phoenix and Flagstaff. And it has to deal with tectonics, which leads us into what I believe puts the rad in Colorado, the Colorado Plateau, which due to its extraordinary geology, there's nowhere else like it anywhere on Earth. This layer cake of geology, uplifted, preserved, relatively undeformed, lifted all of these rocks and then has been eroded recently, has left behind the highest concentration of national parks and national monuments anywhere outside the Washington, D.C. area. So all of these beautiful national parks and monuments just right here around Flagstaff, Walnut Canyon, Sunset Crater, Wapatki National Monument, with places like Petrified Forest, Grand Canyon, Canyon de Chelly, many places on this area because all of these sedimentary rocks were uplifted rather mysteriously, not really understood why, but believed having to be from plate tectonics. It is believed that a oceanic plate in the Pacific Ocean subducted under the North American plate, and that caused the crust to rise and buckle up and form the Rocky Mountains, but lifted this area, these four corner states, relatively straight up, leaving these beautiful layers of rocks that were deposited for us to see at this point in time. If you had a time machine and you went back in history a few million years ago, or a few million years in the future, the landscape would not look the same. We're just at a very special time right now to be able to witness this. a list of some of those national parks and monuments found in the Colorado Plateau. And to help understand how we have all of these beautiful national parks, this diagram shows the grand staircase. And we can see this layered cake of geology model where we have all of these different layers spread throughout the region, extending. This would be going from Arizona up to Utah. And in Arizona, we have older rocks. When you move north into Utah is where you get to see the younger rocks represented in this grand staircase of sedimentary rocks that have been folded and faulted and cut and carved by water and erosion and forming all these different canyons. Another geologic principle to help understand in geology is something known as the law of superposition and the law of original horizontality. So the law of superposition I could explain when I was an instructor. If you were turning in an assignment as a student and your professor had a stack of papers on their desk and the student wanted to turn their paper in to think that it was turned in on time or early, but they were actually turning it in late, where would they put it in the pile? You'd put it on the bottom because you think the ones on the bottom got there first and then gradually the ones on top stacked up later. Same principle with rocks. We can infer with sedimentary rocks, rocks on the bottom are older. When you build a house, you build the first story before you build the second story, and so on. So rocks on the bottom are older, rocks on the top are relatively younger. So if you're at the Grand Canyon and you're looking down, older rocks below you, at your eye level or just below your eye level are younger rocks. And as we move to the north, in Utah, the rocks get younger. And the reason it's not just all horizontally flat throughout, because there's been different faults and different uplift mechanisms from plate tectonics that have moved these layers around. Then the law of original horizontality in sedimentary rocks means when we think of these sedimentary rocks either forming in oceans or pieces of other rocks such as in rivers, deltas, beaches, sand dunes, changing environments, they would be relatively spread out flat and horizontal. The key to the past is written in the present. Where you see modern day sand forming, that's likely going to be a sandstone one day. Where you see a modern day coral reef, that's likely going to be a limestone one day in geologic time. So we can infer that these layers were spread out over vast regions, not just like one isolated volcanic lava flow. So these are some important concepts to understand as we move along. And then as we're focusing on Arizona, just to get a little bit look at where our geology is here, this blue dot represents where the Flagstaff area is here, this blue circle. In this topographic relief, you can see how diverse the landscape of Arizona is. So any point in Arizona, if you don't like the weather, just drive a couple hours. You'll be in a completely different landscape, environment, most likely elevation change, and you can find a totally different weather and climate zone. And then this nice little touristy map here showing our relative proximity to the Sedona Oak Creek Canyon area in the Verde Valley with this yellow circle. So Sedona and Flagstaff are relatively close to each other. I think something only about 40 miles away. And looking at Sedona and Oak Creek Canyon, those layers you see there are the layers that are below our feet here in Flagstaff. But Flagstaff has a volcanic history, which we'll talk about as we move forward. So to understand the geology of northern Arizona, we're going to focus on Sedona because Sedona is beautiful, and why not? Because all of these layers are very beautiful, laid out on display as you descend down into Oak Creek Canyon, which was formed by a fault. So showing our relative proximity that we have these volcanoes in Flagstaff sitting on top of these sedimentary layers in Sedona that are just below our feet. As we're trying to understand the Sedona and Flagstaff area, it's also related to the Grand Canyon as well. Some of the same rocks you see in Sedona, you see in the Grand Canyon. And to help understand that, some of these maps here that were put together by a former NAU geology professor named Ron Blakey, who interpreted what the Earth would have looked like at the time some of these rocks would have been forming. So over geologic timescales, the plates of the earth move around, sea levels rise, sea levels fall, and therefore different continents are formed. And there's glaciations, and the earth is just changing over time. This shows what the earth may have looked like around the time many of the red rocks we see in Sedona and the Grand Canyon were forming. At this time, the area that is now known as Arizona would have been at about 7 degrees north of the equator. So we think, what's 7 degrees north of the equator now? Tropical areas in shallow seas. And this would have been the western edge of what would become the North American continent. So part of the reason our geology is so special here is because we were on this continental edge, right along an ocean that was rising and falling over geologic time, depositing different rocks in different colors in different layers. So part of what makes the Grand Canyon so grand is these changing environments. We don't call it the mediocre Grand Canyon. There are canyons on Earth that are bigger, some that are wider, some that are deeper, but the vast display is there because all of those different layers in different colors, different patterns, different textures is because they were formed in different environments at different times, right on the edge of a continent, in a much warmer tropical environment. And this shows some of the main layers that you see in the Grand Canyon. And this reminds me there is a mnemonic you can help to remember the stratigraphy of the Grand Canyon. And that is, know the canyon's history, story of rock made by time. And that's because we have the Kaibab limestone for the K for the know. The T is the Toroweap Formation, the canyon, Coconino Sandstone, history, Hermit Shale, know the canyon's history, story, which is the Supai rocks, know the canyon's history, story of is just a placeholder, know the canyon's history, story of rock, Redwall limestone, made by time. We have the Moab limestone, Bright Angel Shale, and Tapete sandstone. When I was teaching Geology 101 at NAU, I thought it would be a good idea to have students come up with their own version of a mnemonic. And I quickly learned that the next time I did that, I had to specify, please don't make it R-rated. Try to keep that G to PG rated, because the college students can get very creative coming up with their own mnemonics. So there won't be a quiz on that, but you can remember the layers of the Grand Canyon. And what we can see here, most of the layers that we do see in the Grand Canyon are what's known as the Paleozoic layers, because they formed in the Paleozoic time span. Starting in the Cambrian, which was about 500 million years ago, up to the Permian, which was about 250 million years ago. So about a couple 100 million years formed most of the layers we see in the Grand Canyon. There are older layers below that, with one interesting feature in the Grand Canyon, something known as the Great Unconformity. Who here has hiked down to the bottom or been through on the river on a raft? So you would have seen this. When you get to the bottom, there are these basement rock layers, because they represent the basement of the Earth, that are about 2 billion years old. Above that are sedimentary rocks about 500 million years old. So over 1 billion years of geologic time is missing from the rock record, and it remains a bit of a mystery of how those rocks got there. No one really knows, but it's pretty cool to keep that mystery out there, to keep us wanting to learn more and make new discoveries of trying to understand why that is. So when we compare the rock layers we see in the Grand Canyon to the rock layers of Sedona, we can see we have a lot of those same sedimentary rocks in the same places, except Sedona has one extra special one known as the Schnebly Hill Formation. So if we were to modify that mnemonic, instead of just saying story of rock, we would say Sedona story of rock for the Schnebly Hill Formation and the Supai Formation. So a lot of these same rocks you'll see there, and we have in the Sedona area the geologic time period known as the Mississippian, where there is a Redwall limestone below your feet in Sedona, and then at the very top of Sedona is another formation called the Kaibab limestone, separated by many millions of years of geologic history, And this is one thing that helps preserve the geology of Sedona, why it's so spectacular to see. A lot of those mudstones and sandstones are very easily eroded, but that limestone on the top and that limestone on the bottom kind of makes it a limestone sandwich. And that limestone is more resistant to erosion and helps preserve these layers. So here's an example showing some of the same rocks you'll see in the Grand Canyon, you'll see in Sedona. They might have slightly different names in some areas. And when the geology of Sedona was first being studied, it's relatively understudied for such a fascinating place. Early geologists who studied it in the 40s just were calling rocks Supai A, Supai B, Supai C, assuming it was the same layers they saw in the Grand Canyon. But in more recent years, starting in the 70s with NAU professor Ron Blakely and others, they made discoveries that Sedona has some of its own story with this Schnebly Hill Formation in Sedona. And to understand the geology of Sedona, and therefore northern Arizona, as Sedona is a place we can kind of grasp because it's one location, we have the deposition and formation of rocks, then the uplift of the Colorado Plateau, and then lastly, the differential erosion and faulting, which leaves behind the landscape that we see today. So we'll go back to the beginning in the Pennsylvanian era about 300 million years ago. And to put this into perspective, we think dinosaurs are old. This time period on Earth is before dinosaurs. And this map here is a depiction of what the landscape may have looked like at the time. So Arizona was the western edge of what would become North America, with seas rising and falling, deposited different rock layers in different units. And this would give us the Supai group. We call it a group, not just one rock type, because as the environment was changing, many different layers of sand and mud and limestone were being deposited, being close to a sea level, rising and falling. We can think of this like a river delta, maybe something like the Nile River, where it's flowing in a desert area, depositing rocks and moving around. Then we get to our next geologic time period, known as the Permian period. So we've all heard of Jurassic Park. When we think of Sedona and the Grand Canyon, we can think of that as Permian Park, because a lot of the rocks that we see, the really beautiful ones, are from the Permian period, about 250 to 299 million years ago. And this red square shows about where Arizona was at the time, right on the edge of that continent, showing what it may have looked like in the early Permian. So most of the beautiful red rocks and formations formed about 275 to 285 million years ago. And above the Supai Formation in Sedona, there's something called the Hermit Formation. About 280 million years ago, where the current day Rocky Mountains are, there was another mountain chain called the Ancestral Rocky Mountains. We can think of that as being the prequel to the current day Rocky Mountains. The rocks from those mountains were eroded, left behind sediment. They washed down to the southwest, leaving many red rocks behind. You see red rocks in Durango, Colorado, Moab, Utah, Taos, New Mexico. A lot of these red rocks are from those ancestral Rocky Mountains. And by the time they got to the Sedona area, it was mostly shales and fine-grained sediments. So most of the city of Sedona is built on this shale, this Hermit Formation, because it's a soft sediment that's easily broken up. You can build on it. The Oak Creek can cut through it. And most anywhere in Sedona you see trees, junipers and piñons, it's most likely going to be on this Hermit Formation. The next layer in Sedona, which is a really special one, the Schnebly Hill Formation. This is going back to an edge of a continent with rapidly changing sand dunes right on the edge of a continent, leaving behind different color rocks that in geologic time formed rapidly. So anywhere in Sedona, if you see a rock with a formation name, such as Cathedral Rock, Bell Rock, Snoopy Rock, Coffee Pot Rock, it's most likely going to be the Schnebly Hill Formation. And when you're hiking in Sedona, you can look for this layer called the Fort Apache limestone, which is about a 10-foot thick band of a darker gray rock within the red and tan sedimentary rock that kind of looks like a bathtub ring going out all through Sedona, and that represents a sea level rise that deposited some limestone, forming this bathtub ring. The next major geologic time period we have is, or the geologic unit we have is the Coconino Sandstone. And this leads us to a good question: why are the rocks red that we see in the Southwest? Anyone know why our rocks are red? What is the culprit? Iron, yes. So it is iron, as sedimentary rocks are eroded remnants of other rocks, such as granites and mountains that had iron in it. That iron gets washed downstream and forms in sands and sandstones and sedimentary rocks. That iron rusts and forms a red color. There's not enough iron to mine it. It's in very small amounts. It only represents about 0.5% of the rock's weight is actually iron. And we can't just use color to identify a rock. Often texture is the best feature. And that's because the same rock can be in different colors. And a great example here is our explanation of the Coconino Sandstone. If you see a rock layer that has these horizontal, about 33-degree angle crossbeds in them, or striations, linear features, what you're looking at is fossilized sand dunes. This area at the time was a big sand dune area, something similar to the Sahara Desert of North Africa, big windswept sand dunes. And when the wind moves sand, it moves mostly quartz and mostly large particles of quartz, large for sand, that is. So all of the finer grained sediments like mud and silt get washed away. And then these sediments, when they're interlocking, if you looked at it under a microscope, you could see there's space in between these sand grains for water and fine grained sediments to flow through them, which makes the Coconino Sandstone a good aquifer. And then below that, they get trapped in the layers below that, where the water can't flow easy, and the fine grained clays and silts get trapped in there, and all the iron that got washed away ends up in the layers below it. So that's why if you're driving through Oak Creek Canyon or hiking in the Grand Canyon, you see this layer that has these horizontal beds in it at an angle. Those are the sand dunes, as the wind marched the sand up to an angle. And then based on the structural integrity of sand, always about 33 degrees. So if you get that in a trivia question, you got it right there. And then forms these angles forming that sand dune, so you can identify the Coconino Sandstone by the presence of those layers. Then we have the Toroweap Formation, which represents a transition from that Saharan Desert sand dune area back to the ocean rising to forming the Kaibab Formation, which is mostly a limestone that formed under the ocean. An interesting fact, the word Kaibab is a Paiute term that meant upside down mountain. This is what the Paiute people, in my understanding, would call the Grand Canyon, and they were very accurate in that, as it is an upside down mountain when you think about how all of those layers of sediments got there, most likely from mountains that were eroded and transported in to wash in there. So this Kaibab Formation, as it formed in an ocean, you can find a lot of marine fossils in here. So don't expect to find your Tyrannosaurus rex. It's still older than the dinosaurs, but you can find things like shells, mollusks, bivalves, coral fragments, things like that. And that's throughout the Colorado Plateau region. When you're at the Grand Canyon, south or north rim, and you're looking down, the rock below your feet at the upper layer at the visitor centers is the Kaibab limestone. So the main rock layers we just discussed. Now we're moving into the uplift of the Colorado Plateau. As the plate tectonics were converging, it caused the crust of the earth to buckle, causing all the rock layers to form in this great layer cake of geology, leaving it to be cut by rivers and mountain rivers later and other processes of erosion. Then how did we get to see this beautiful landscape of Sedona? Why is it just not all a flat landscape? Well, it has to deal with erosion and differential areas eroding faster than others, volcanoes, and earthquakes. When you're in Sedona and you see the cliff edges to the north, that represents the edge of the Colorado Plateau. In about the last 5 to 10 million years, the Colorado Plateau has eroded about 4 miles, What is now the village of Oak Creek in South Sedona is where the Colorado Plateau used to be, and that's why we have all those different formations, those cliffs, those buttes, those mesas. It's the eroded remnants that did not get eroded away. And then we have faulting and earthquakes that left behind Oak Creek Canyon. And then the reason Oak Creek is always running in water is because all of the precipitation in northern Arizona, such as the snowmelt and Flagstaff, soaks into the ground. As Arizona in general is not known for many rivers, and not much in northern Arizona outside of the mighty Colorado, that water soaks into the ground and comes out as springs in lower parts of southern Arizona, such as in Oak Creek Canyon. And that creek acts like a conveyor belt to help wash away the sediment and move the sediment downstream, just like the Colorado River forming the Grand Canyon. You can think of it as kind of a muddy sandpaper that is moving the sediments away, eroding, and moving them downstream at the same time, moving something like 500,000 tons of sediment downstream every year. When we think of the Colorado River, it's only about 100 yards wide, but as it's moving and meandering and washing away sediment, it can cause the canyon to expand over time. Then the next phase of our geologic history of the Flagstaff area is our beautiful San Francisco peaks. And the way these got here, to my understanding, remain a bit of a geologic mystery. I'm not a volcanologist, but Greg is back there, so maybe he can correct me if I'm wrong. But it doesn't really make sense why we have all of these beautiful volcanoes here in Flagstaff. Most places in the world where you see volcanoes, they're on plate boundaries, where one plate is subducting under another or converging, spreading apart. Places like Iceland. We can think of the Pacific Northwest Cascades, Indonesia, the Ring of Fire. But we're in the interior of a continent here. So the explanation is a mantle hotspot. Just below our feet, the mantle is active. And when it acts up, heat rises, melts the crust, and forms volcanoes. So any of the hills or mountains you see around Flagstaff are probably volcanic features. The area is known as the San Francisco Volcanic Field. It is why Flagstaff is so high in elevation. If you drive to the north or to the Four Corners area, the landscape levels out and is relatively flat. All the hills here are lava flows. There's something like over 600 volcanic features in the San Francisco Volcanic Field. So many, they don't even all have names, just numbers. And this hotspot is believed to have began in what is now the Williams area and is migrating to the northeast. So again, to use my hands as an example, if my left hand represents a hot spot and my right hand is the North American plate moving over it, as the plate moves and the hot spot stays in the same place, that heat can break through the crust and cause volcanoes to form. And another interesting thing about the San Francisco Volcanic Field is the diversity of volcanoes that we have. Many different types of lava flows, lava tubes, different mountains, stratovolcanoes, shield volcanoes, dome volcanoes, many different types of varieties of volcanoes all in this area right here. And this diagram here shows these volcanoes coming up from the sedimentary layers below our feet. So if you're here in the winter and you're driving up Cherry Hill and there's snow and you're struggling to get up it, you can thank the volcanoes for that. This shows some of those volcanic areas that we can see here. This crater out to the north of here, known as SP Crater, named by the old ranchers, where the P stands for pot, the S stands for a four-letter word I'm not going to say. And that's because they were ranching out there and they didn't know what to make of this landscape, but they know their cattle didn't like to graze on it. So this 3D topographic map shows where we are with the San Francisco volcanic field. A great question about this: is the San Francisco volcanic field considered extinct, dormant, or active? Anyone want to take a guess? It is considered active because in geologic time, it's not that old. There was an eruption at Sunset Crater National Monument only about 1,000 years ago, where there was prehistoric people living there at the time. And there's artifacts in some of the lava flows there from that. So in the year 950, only about 1,000 years ago. And the San Francisco volcanic field could erupt again, but if it did, it likely would be a cinder cone out to the north and east in a low populated area. So it likely would not be a catastrophic disaster movie like we often see geology depicted, but it would be quite the sight to see. Another interesting aspect of the San Francisco volcanic field is its relationship to the Apollo astronauts and the Apollo space program. This building you're sitting in here is called the Shoemaker Building. It's named after Eugene Shoemaker, who was a geologist who helped train the Apollo astronauts in the 60s and established this building known as the Astrogeology Center. Now we call it planetary science, but at the time they were calling it astrogeology. And based on the landscape of northern Arizona, the volcanic features, the cinder cones, the lava flows, what they thought the moon was made out of, they made terrain around here similar to what they would find at the moon and brought astronauts here to train them. So this great news article, One Small Town, One Giant Leap, explaining Flagstaff's role in the Apollo moon landings, with current astronauts training currently only in the last couple years for NASA's attempt to return to the moon in the next few years. And then I'll just talk about a few highlights of geology in the area that we can wrap up. Another one is Mount Eldon, which is right out here. You can see right outside this building. We get to see her every day. Who here has hiked this mountain or been around it? A lot of hands up there. So this mountain is very steep. It's a tough hike. And why that is because of the type of volcano it is. There's volcanoes that flow, like we see in Hawaii, and then there's the volcanoes that go boom, like Mount St. Helens. And it has to deal with the silica content in the lava, in the magma. If there's more silica in it, it does not flow. It can just build up pressure and form steep mounds of material. And this Mount Eldon is that more silicic type of lava. There's dacite, and when that rock erupted, it built up pressure, it formed a mound. It was viscous, meaning it could not flow. And just like when a tea kettle starts going off, all that pressure eventually escapes and forms a volcanic eruption. And that's what it kind of looks like, a crater when you get a view out from the side. From the aerial view, you can see some of those lobes of lava. And that explains why that mountain is so steep to hike, because that lava just mounded up. Some geologic highlights we have in the area: the petrified forest, which we are getting to younger rocks that formed in the age of the earth when dinosaurs were around. Some of the most beautiful, best preserved petrified wood of anywhere in the world. Who all has been there? Quite a few. That is awesome. It's really a spectacular sight to see right here in our geologic backyard. Another place, Meteor Crater, on that way going east on the I-40. Meteor Crater closer to Winslow. The best preserved impact site of anywhere on Earth because it was formed only about 50,000 years ago in this arid landscape. So it hasn't been eroded away. There hasn't been plants or trees to grow over it. Part of the reason the NASA Apollo astronauts came here was also to look at this interesting feature around here too. And another spectacular area out here to the northeast, an area known as Grand Falls, where there's a waterfall that can form seasonally with snowmelt that has waterfalls that are bigger than Niagara Falls, really beautiful, known as Chocolate Falls, which was formed from a lava flow, changing the direction of water and causing a steep escarpment to form as the water changed directions. This place is currently off limits as it is on tribal land, and it's only available for tribal members now, but it is a beautiful place representing the geology of the region. And with that, I just want to give a few shout outs, a few thank yous as we wrap up. Professor Ron Blakey, who's at NAU, he made a lot of the diagrams and landscapes to depicting what this area would have looked like hundreds of millions of years ago. And another geologist who is in Flagstaff, studied at NAU, works mostly as a guide, but does talks and lectures. I believe he's affiliated with the Museum of Northern Arizona, Wayne Ranney, and he wrote a book on the geology of Sedona, which where I got a lot of my information from. So to wrap that up, I want to give a quick shout out to all the sponsors again. Give another bit of encouragement to fill out the survey when you can. And with that, I would like to say thank you and answer any questions.